I have to be grateful for this invitation. Is there echo?
There's a little bit of echo.
Yeah. Okay. I thank WeBIOPATR organizing committee for and scientific committee for allowing me to present my work. I have many co-workers that I will thank during my speech. Here I am to present after the big picture that has been presented this morning, very relevant and dealing with well-known parameters of air quality. I'm here to present some experimental details that are relevant for environmental issues related to particulate matter and aerosols that are of emerging interest and are touching us all. My little presentation, I graduated in chemistry. I have gotten a PhD in strange thing, commodity science. I'm associate professor at the University of Trieste, teaching environmental chemistry, analytical chemistry, and risk assessment of chemical. I'm appointed national expert at the European Standardization Committee in some groups dealing with odor nuisances, but recently also in the Technical Committee 28, which is related to bioaerosols, related both to detection of bioaerosols, so biological microorganisms in ambient air and in emissions. Within the International Society for Olfaction and Chemical Sensing, I met Saverio De Vito, who I thank for introducing me to WeBIOPATR, something I'm also connected with UK Aerosol Society. During these days, I'm really happy because I heard many interesting things about the issues that I'm dealing now, or I've dealt. I'm supporting the administration of my region, which is called Friuli Venezia Giulia, nothing more than 1.5 million, less than 1.5 million people close to Trieste. And we are defining the upgrade of an air quality improvement plan. Yesterday we were talking about environmental justice, and I've been consultant both for public prosecutor office and for the mayor of Trieste in some quarrel between steel plant and community of people around this industrial plant. So in that case, I dealt deeply in PAH, polycyclic aromatic hydrocarbons, coming from coke oven, and also another activity that we had was on emission factor from wood burning stoves, managing kind of dilution tunnel. Well, beside everything, now I'm coordinating a multidisciplinary research group on infectious aerosols, and that's what we will talk about. First, presenting some first studies that started handling data produced by others, and then we present some analytical studies related to sampling, and so this lack of standardization in methods for collecting data on SARS-CoV-2 RNA presence in particles, and more on infectivity detection, residual infectivity detection on aerosol samples. So it is not very much important to find RNA dispersed around, but it is relevant to understand if the samples, the aerosol samples, are still infected. And for that, we managed to reactivate biosafety level 3 lab for putting, say, some studies in control situation on SARS-CoV-2 infectivity in aerosol, in very fine aerosols. With the expertise we had, we moved to healthcare units, both infective, say, ward and on geriatric ward in the hospital around us. I would talk briefly about technology, which is quite sensitive for point of care detection of SARS-CoV-2, and that's the picture. So how did it start? In February 2020, Italy has been hit by a pandemic, and what happens is that a bunch of former young researchers in analytical chemistry were hit. So some of us, people living near Bologna in Medicina, were the first municipality that was closed, isolated in Italy on early March 2020. But then other friends of us were in Bergamo, which gained the honor of New York Times first page as the heart of the coronavirus outbreak at that time. And we started just with some hypotheses showing that, say, it was because several elders of the municipality of Medicina, close to Bologna, were together in a social event, cooking polenta or something like that. And in a few days, in this, say, smoky environment, a few days they were all died. And this was a sad event that pushed us with position paper relating a number of exceedance of PM10 threshold value, put in relation with a number of, say, infected people in the beginning of this outbreak, meaning that no one was using masks, there was no lockdown. And so we found some kind of relation. This has been transformed in a research paper that has been published in British Medical Journal, in which a friend, being strong in statistics, helped us to give a form with a logistic regression relating the ratio between cases and population and the number of exceedance of PM10 daily value, say, in different provinces. The white one are North Italy, and the black dots are, say, Southern Italy. This was just dealing with numbers produced by others. And a relevant step has been handling experimentally filters of particulate matter and looking for presence of SARS-CoV-2 RNA. This was the first evidence that has been produced. And so thanks to friend an environmental genetist, Alberto Pallavicini of the Department of Life Sciences of the University of Trieste, we had evidence of presence of both, say, different genes, DRP gene, E gene, or also N gene, detected in this dirty PM10 filters. It's not so easy to extract RNA, which is very delicate biomolecule, from a very dirty PM10 from Po Valley, which is totally black with carbon and different things. This was the beginning. Then a lot of say, literature has been produced. How many studies are experimentally sound? There is a clear request of understanding airborne transmission also with experimental data. There are some effort for providing methodological approaches, because many papers are using totally different way of sampling, extracting, handling say, this RNA, and even with more difficulties extracting viable viruses. So the issues that we can see are how to sample PM or aerosol for RNA detection, how to sample for detecting residual infectivity from aerosols, how to conserve and pretreat PM, and then how to detect infectivity. Infectivity is usually assessed by putting samples in contact with the cell lines, but which cell lines? There is no, say, standards, internationally agreed standards on this topic, which are very, very relevant. Beside many speculation, a lot of literature production, on the whole, there are still little data available, not so, so the number is little in comparison to the relevance. This is relevant also for testing both exposure scenarios and for assessing the containment strategies and technologies. And what I'm seeing is that devil is in the details. So we should follow, as an analytical chemist, I go for that, follow the details, because little differences produce very often zero detection. You do not find anything. So put the working shoes and meet the person on the front line and enter in the field. This is my approach. We went in the hospital. So when I talk to hospital people and I say, hey, we are able to detect SARS-CoV-2 in the air, they told me, you miss infectivity assessment. I want to evacuate an hospital just because you are finding pieces of RNA in the air. Is it infected? So we started collecting, say, PM in a geriatric ward in an hospital, and then we reactivated a biosafety level 3 laboratory. There, thanks to co-workers, we started to assess virus replication evidence both by real-time PCR and by cytopathic effect. And so looking at plaque that are formed when, say, infectious virus is put in contact with a type of cell line that are known as Vero E6. There are kidney cells from monkey. And we were looking at what kind of cycle threshold for real-time PCR allows, say, infectivity and show this plaque formation on the cells. So me going into this, say, ward, infectious ward, and what we have seen is that there were no cytopathic effect on these Vero cells for samples with a cycle threshold greater than 24. That means for number of copies lower than 2 to the 10. This is make me thought, so many copies needed. I don't know. So these were some results, and we started to think about what is why there is so much debate on this, say, RNA detection. We started to evaluate some points that are relevant for the detection of this RNA, and what maybe the colleagues, analytical chemistry colleagues, can appreciate. One point is the recovery. How many RNA, how much RNA I can, say, extract from the filters. Different, say, factors are relevant. We tested, we spiked the filters, both virgin filters and say filters hosting PM10 with both some RNA standard from European reference material and also some SARS-CoV-2 inactivated by UV. Then samples were preserved at -80 degrees Celsius for some days, and we tried to see how much of the initial deposited RNA was, say, collected. This is relevant because there are several, say, studies using these quartz filters, and then many of them found no RNA in that. They say there is nothing on these filters. We have found, and so we were thinking why we are finding and they not. Now, this was on quartz filters. It's much easier on Teflon filters. We are preparing a paper to be submitted to atmosphere. And what is fun is firstly that we are able to detect only inactivated SARS-CoV, RNA from inactivated SARS-CoV. The standard RNA is not a good, say, analyte to extract, is too labile. And the recoveries are very low. So we started from 9 multiplied by 10 to the 7th, and we miss at least one log. So we have a recovery of 2%, more or less, in average. And what you have seen is that there is a relevant effect of preservation of, say, these filters in the freezers. So if you are fresh, you extract something. If you keep it for a few days, you miss almost everything. So maybe that so there is urgent need, since many of the ones that were finding nothing preserved in cold, this can be an effect. So just to say that there are several aspects to set up. Another is for assessing infectivity, cellular models are used, and the recent review show that the most of the studies are using these kidney cells as VERO-E6 and other liver, respiratory callus cells and other. But since the very beginning of the pandemic, we know that, say, SARS-CoV-2 multiplies when you have both ACE2 gene and also this other gene, which is a TMPRSS2. It means that the cells link SARS-CoV-2 by ACE2, and then the infection is triggered by an enzyme that is in this other gene. And for instance, VERO-E6 has no TMPRSS2. It means that using these VERO-E6 cells is not a sensible way of showing infectivity. You should have some genetically modified VERO-E6 in which you add this TMPRSS2 gene. So this is very issue in a medical sector. Imagine that paper of Hoffman has 7,2022 citation, so it's very well known, and it's from April 2020. So no one is using this modified TMPRSS for detecting infectivity. Again, so we are underestimating a lot infectivity in environmental samples using this standard Vero is 6. Okay, this was a point for saying we need defining standards. It has been a long debate also on relevance of aerosol, as Lydia Moraska yesterday showed well. Till May 2021, it was thought that droplets were the major, say, vector for SARS-CoV-2. We have assembled, say, a benchmark for showing transmissibility of SARS-CoV-2 in aerosol of particles smaller than 5 micrometers. This was possible because we were engaged in this testing of surgical mask according to EN 14603, testing of chirurgical mask, and we learned how to aerosolize microorganisms, for instance, Escherichia coli, and then collect them in a multi-stage impactor, keeping viable microorganisms. This was possible thanks to collaboration with molecular biologists that came into my group. And with this, thanks to the Italian Society for Environmental Medicine, we've got more sophisticated instruments as this aerosolizer that allows effective and gentle aerosolization. Then we started to collect with this impinger, which put the particle in the flow, say, in contact with a collection liquid surface that generate turbulence that doesn't stress too much, say, the virus. And okay, we generate aerosols with small dimension with one mode at around 0.4 micron, so and another at around 2. So everything was like this. So generating viral aerosol, transmitting it, and collecting, and then what is collected is put in contact with these cell cultures, and also can undergo to RNA PCR detection. So we have seen that this small aerosol can also say an exposure of 5 minutes of aerosols can produce an increase of 2-3 logs in 7 days. So the collected say sample contain viable SARS-CoV-2, and this is for particles smaller than 2.5 micrometers as an evidence. But beside this datum, which is simple, is that this is a kind of support from biological filtration efficiency. So we can put at the end of this transmission tube mask or tissue or whatever, or and we can see if lively virus capable to replicate can pass. Okay. The issue of finding say the virus in a real environmental sample is not so trivial. We started to use, and we got, thanks to a foundation that gave us this these instruments, we used this technology which is called water vapor laminar flow condensation growth tube for collecting the smallest particle with say viable microorganisms. This Vivas sampler has a high efficiency in collecting particles smaller than 300 nanometers, while the other one 0.3 micron. The device is like that, is distributed in Italy by a firm, and then Aerosol Devices, the producer. We tested also another technology, which is this BioFlash biological identifier, which is a point-of-care device using genetically modified lymphocyte, and I will talk about that. The Vivas, or this condensation growth tube, is the technology that allowed Lednicki and co-workers, Chanyu Wu in principle, to collect samples of viable SARS-CoV-2 in a hospital from Florida. The idea is that the airflow is passed through, say, a tube which has a wetted, say, how is it? Wall, okay, wetted wall, and a different temperature. So in the initial phase, the humidity is equalized by cold section. Then you have a very hot section, more than 35, at least 35, so that you create a supersaturation environment. And also the smallest particles grow. You win, say, the resistance, and you have a bigger particles starting from lower particles. And these are collected in a Petri dish in which you have, for instance, viral transport media. It's a good technology for not having impact or shear force on the microorganism to collect them alive. The other technology that I was talking about is this cannery, developed in a Lincoln laboratory at MIT, in which you have B cells that are lymphocytes that are modified, having an antibody on the surface. The antibody is selected by on the basis of which kind of organism you are interested in. They started with the Yersinia pestis, and now they are using antibody for SARS-CoV-2. Moreover, this lymphocytes has this green fluorescence protein that when you have, say, an antigen of the microorganism captured, you have some light emission. The instrument, say, sample 480 liters per minute, and there are also part of the disk which host these sensitive cells that are, say, free for taking the sample for confirmation by real-time PCR. So again, in the infective disease world, and what we have seen, we never detected infectivity, but we found RNA in all the rooms of patients having threshold cycle lower than 20. So it means that not always you have mission again, and more a relevant point is that the air treatment in the hospital is quite effective. You have a very little number of, so you can see here, gene copies per sample, or gene copies per square meter, cubic meter, sorry. In the worst case, we're in the order of 600 or 700 from 600 copies for square meters. Okay, this has been done also in other words. Just to conclude, we have a kind of a device that can be used for testing viral filtration efficiency. We are testing low flow technology for handling, say, for treating, for sanitization of air, thanks to collaboration with the engineering department of the University of Trieste. And we have some problems in handling high flows. It means hundreds or thousands of liters per minute. We are going to apply our expertise in metagenomic of air samples, in particular in wastewater treatment plant where you have aeration of the flows. This is really an interesting point for community sentinel, in which the wastewater collected in a community are generating big aerosols, and you can sample in continuous way, not as when you sample liquid waters, in which you make small partial samples every hour. You collect something, but in this way you can collect all over in filters or other devices. And this experience, of course, now started for SARS-CoV-2, but we are very much interested in antibiotic resistance and other viruses that are on the way. Okay, this was say the device that is a kind of optimized filter in which we put also a LED, UV LED. And so you can have a very good sterilization of the airflow with a little resistance. It is not a HEPA filter, so which block requires a lot of energy for making pass air, and this is something we are working. We all this as zero finance, zero projects. It is just a research initiative moved by need of understanding something and providing our contribution to the society. I have to thank Sabina Lichen, which is a researcher in chemistry, Semeraro, Sabrina, which is a biologist with Duping as a biologist, Maria Grazia Perrone from Tecora, that was mentioned before, is an environmental scientist. We have a Professor Sima, infectivologist, Professor Libera, two big help that I have in the hospital that are Francesco Fontana and Maurizio Ruscio. Thank you for the patience.
Thank you very much. Pierluigi, maybe just one quick question so we can move on to the next. Rock Novak had questions, but Rock, if you're in the room, will you just pose them yourself?
Please.
Rock, his question.
Sorry.
Oh, there's an echo.
Yeah, I hope that you can hear me now. Well, you can hear me now. So my first question would be, what is your reasoning or speculation why the detection of RNA fell so rapidly after just a day or two, even at -80, and would even lower temperatures help with that?
You have a silica acidic surface, and then it is an open issue, but we want to share this, and other also researchers are saying that the integrity of RNA is really an issue. They are not very stable molecules. This interaction with the surface really can denaturate. We have some hypotheses, but we will say, okay, go on. Say there are theoretical studies showing interaction between OH from the surface and this RNA changing somehow the structure and then making it not detectable anymore.
All right, thank you. But maybe, Rock, you had another question. Maybe you can save that since you're both in Belgrade to chat in the break. But in interest in time, so we can move on to Clara. And then you're privileged to have opportunity to talk in person later. And Simon says also thank you for a most excellent talk. And same here. Impressive amount of results